Welcome to Mathematics for Machine Learning. This is the start of chapter 2. So to start off, the first concept that you need to understand is the concept of algebra. So what is algebra? Algebra is a way to formalize intuitive concepts. To make it more concrete, a set of objects, so a set of objects and a set of rules to manipulate those objects. So if you have these two things together, set of objects and a set of rules that you can use to manipulate those objects, that's what algebra is. And linear algebra, that's a study of vectors and the rules to manipulate those vectors. So that's what linear algebra is. Set of vectors and a set of rules to manipulate those vectors. So what do we mean by vectors? Now, any object is a vector if they follow two specific rules. Those are the rules of addition and scaling. And to make this more concrete, think of a vector A. So let's think of it in a two-dimensional space. So let's call this y, x and xy plane, and think of A. So this is a vector A. Now, if I have another vector B. Now, if I add vector A and vector B, the result would be I'll get a third vector, well, a vector C, which is an addition of vector A and vector B. So this is the rule of addition, and the rule of scaling is I can have any scalar, and if I multiply that with a vector A, the result would be, let's call this another vector, which is essentially a vector which has either lengthened or shortened depending on the value of the scalar. So if I have an object and it follows these two properties where you can add and where you can scale, and the result is an object of the same type, then that means that it's a vector. So the concept that we are most familiar with is the geometric case, an example that I just presented, where you can plot a vector in a two-dimensional space or a three-dimensional space, or you can use that intuition to visual or think of a vector in more than 3 dimensions. But there are these other examples that follow the two rules, addition and scaling, and that's why, based on our definition, they're also vectors. So polynomial. So if you have a function, a polynomial function, it would be any function. So you have this, or think of a different type of function. I don't know if you have this. So these polynomial, these are also vectors because they follow the same rule. You can add two polynomials and the result would be another polynomial, or you could multiply a polynomial by a scalar and the result is a polynomial. So that's why polynomials are also vectors. And now audio signals is another example of vectors because you can have the same two operations of addition and scaling and the result will be an audio signal. Now, the one that is most relevant to this course and the one that we'll talk more about as we proceed, that's this one, elements of Rn. So what do I mean Rn? What Rn means is an ordered set of numbers in n dimensions. So let's go to a clean. So if you have R2, that just means a set or a tuple of two numbers. So let's call this A1, A2. If we have R3, that just refers to A1, A sub 2, A sub 3. And extending this concept, if you have Rn, so it's just a tuple or a set of real numbers, A1, A2, dot, dot, dot. Let's go to An. So this, based on our definition, because we can add and scale any tuple in Rn, then that means that this is also a vector. So these are all different types of, well, these are all vectors. Another important concept in this course is the concept of closure. So this refers to the set of all things that can result from an operation. Now think of a vector A and an operation, say a scalar operation, so a lambda A. We are interested to find out the set of all possible vectors that can result from this operation. And the set of all possible vectors, we would call that a vector space. And geometrically, what this means is if you have a vector A, then the vector space of this operation would basically be a line which passes through A. So this would be the vector space of this operation. Don't worry if this is a bit abstract, because we are going to cover this in more detail in a future section.